All right, welcome back to the deep dive.
Good to be here.
You know, the show where we really try to get into the details of the online encyclopedia of integer sequences.
It's an amazing resource.
Absolutely essential, I think, especially for number theory students listening in.
Definitely.
And today, well, we're tackling one that looks pretty straightforward initially, but it's got some surprising depth. Sequence A000196.
Yes, A000196. Fundamentally, it's, well, the integer part of the square root of n. Seems simple.
Right.
But what's really interesting is how many different mathematical ideas seem to lead right back to this very sequence.
Exactly. And the OEIS itself gives us a few ways to think about it right off the bat.
Mm-hmm.
The integer part of the square root, like you said. Then the number of positive squares less than or equal to n.
Okay.
And maybe the most intriguing one initially,
Mm-hmm.
the value n appears 2n plus 1 times in the sequence.
That last one describes the pattern within the sequence itself.
Yeah.
Yeah.
And just for clarity, the offset, it starts at n0, right? So A0 is 0.
Correct. The sequence goes 0, then 1, 1, 1, then 2, 2, 2, 2, and so on.
Okay, so let's unpack that first definition. Integer part of the square root.
It's really just what it sounds like.
Yeah.
You take your number, n, find its square root, and, well, you just drop everything after the decimal point. The floor function, technically.
So like square root of 10 is about 3.16. Floor is 3.
Exactly. A10 is 3, or take 16, square root is exactly 4.
So A16 is 4.
Precisely. It's the most direct calculation.
Okay, straightforward enough. But then how does counting the number of squares less than or equal to n give you the same result? That seems different.
Well, think about it. Let's use n10 again.
Okay.
The perfect squares less than or equal to 10 are 1 squared, which is 1, 2 squared, which is 4, and 3 squared, which is 9.
Right. 1, 4, 9. There are 3 of them.
3 of them, and what was a 10?
It was 3.
Oh. Yeah. See, let's try n20. The squares are 1, 4, 9, and 16.
4 squares. And the square root of 20 is 4 point something. So the integer part is 4.
It matches again. The integer part of the square root is essentially telling you which perfect square is the largest one that's still less than or equal to your number n. It's counting those square steps.
Got it. Okay, so it's like using 1, 4, 9, 16 as like benchmarks.
Exactly. A kind of ruler based on squares.
Cool. And that third definition, the one about n appearing 2n plus 1 times, how does that work?
That one's describing the structure you see when you write out the sequence. Look. 0 appears once,
Okay.
then 1 appears for n and n, 2, 3, that's 3 times, and 2 times 1 plus 1 is 3.
And 2 appears for n, 5, 6, 7, 8, 5 times.
5 times. And 2 times 2 plus 1 is 5. It holds.
Wow.
In general, the value k appears starting from nk2 all the way up to nk plus 1, 2, 1.
Right, just before the next square.
Exactly. And the number of integers in that range from k2 to k plus 1, 2, 1 inclusive is just
k plus 1, 2k2.
which expands to k2 plus 2k plus 1k2, which simplifies nicely.
And 2k plus 1. There it is.
Precisely. So the value k appears exactly 2k plus 1 times. It's a neat property baked into the sequence's own structure.
Okay, those 3 definitions really paint a picture. But the OEIS, as always, goes deeper in the comments. This is often where things get wild.
Oh, absolutely. This is where you see the unexpected connections that make number theory so fascinating. For instance, Amarnath Murthy points out that an is also the integer part of the geometric mean of the divisors of n.
Geometric mean of the divisors. Okay, refresh me.
Yeah.
Geometric mean is you multiply them all together.
You multiply all the positive divisors of n together, yes, and then you take the dth root, where d is the number of divisors.
Wow, that sounds complicated to calculate. And that gives you the floor of the square root.
The integer part of it, yes. It's quite surprising. It connects the multiplicative structure, the divisors, directly to the magnitude represented by the square root.
That really suggests something deep about how multiplication and sort of size relate in integers.
It does. It hints at this underlying harmony. Then Benoit Cloutier gives another perspective.
Okay.
He says an is the count of numbers k, up to n, that have an odd number of divisors.
An odd number of divisors.
Yeah.
Wait, that happens only for perfect squares, right?
You got it. Because divisors usually come in pairs, d and nd. Unless n is a square, then squartarian is paired with itself.
So counting numbers with an odd number of divisors is exactly the same as counting the perfect squares up to n.
Exactly. Which loops right back to our second definition. It's just a different way of identifying the squares. Beautiful, isn't it?
It really is.
Yeah.
Same result, totally different angle. Then Reinhard Zumkeller, throws in something completely different about number bases.
Ah, yes, the representation in a base where place values are squares. So instead of base 10 with places 1, 10, 100, or base 2 with 1, 2, 4, 8.
You use 1, 4, 9, 16 as the place values.
Right. And Zumkeller states that for n0, an is the number of digits you need to write n in this square-based system.
That's wild. So like the number 12, it's 1, 9 plus 3 ones. No, wait, 1, 9.
1, 9, 0, 4s, and 3 1s. Maybe. It's a non-standard representation, but the number of places used up to the largest square needed.
Seems to relate back to AN. Okay, that's a very different way to view it. He mentions A007961 and A1903212.
Yeah, likely sequences exploring that specific base system. It raises interesting ideas about efficient representations. And there's one more from Anti-Cartoonin.
What's that?
He describes A000196 as the least monotonic left inverse of the sequence of squares, A000290.
Whoa, okay. Least monotonic left inverse. That sounds dense.
It does sound a bit technical. Think of A000290
Was it squares?
Right. An inverse tries to undo that. If you apply the inverse to 9, you want to get 3 back.
Makes sense.
But what about numbers between the squares, like 10, 11, 12? What should the inverse give? A left inverse provides an answer. The monotonic part means it has to be non-decreasing.
Okay, so it can't jump down.
Correct. And Lee specifies a particular rule among possible monotonic inverses. It turns out that this specific, well-behaved way of inverting the squaring function gives you exactly the integer square root sequence.
So it's like the most natural way to step back down from the squares.
That's a good intuition for it, yeah.
Incredible. So many different characterizations. And then, of course, there are the cross-refs, links to other sequences.
Always a gold mine in the OEIS. You see links to A000290, the squares themselves, obviously.
Naturally.
But also things like A002162, which pops up in a formula later, and several others. A003056, A028760, A048766. Quite a few.
What does linking to so many tell us?
It suggests A000196 is really fundamental. It appears in relation to sums, differences, compositions, or properties shared with these other sequences. And it's mentioned as appearing in column K1 of A281871, implying it's part of some larger table or family. For students, clicking through those cross-references is how you discover connections.
Like following breadcrumbs through the mathematical forest. Let's look at the formula section. We've got the basic one, AN, A square, NN.
Yep, the definition in formal notation attributed to Arkadiusz Wasilewski, but then it gets much richer.
Like the generating function. That's where x times the sum of x to the j squared.
Exactly, and that's also equal to an expression involving the Jacobi theta function, theta 3.
Okay, theta functions. Now we're getting into deeper waters. Complex analysis, right?
Right. Generating functions package a sequence into a function, letting you use calculus in analysis. The theta function connection links it to things like elliptic functions, quadratic forms, really central topics in number theory.
It's amazing how a simple sequence connects out like that. And then there's this one from Enrique Perez Herrero involving the zeta function.
Ah, yes. Sum over n0 of 1 divided by AAN to the power s equals 2 times zeta s1 plus zeta s.
Connecting the integer square root to the Riemann zeta function. Seriously.
It's a stunning formula. The zeta function is tied to prime numbers, arguably the heart of number theory. Seeing it related to a sum over the terms of our simple floor sequence, it just underscores how interconnected everything is.
Mind blown a little bit there.
Okay.
What else? Wesley Ivan Hurt has one. A sum involving A000005.
A000005 is Dn, the number of divisors of n. Hertz's formula is An equals the sum from I01 to n of A000005 I mod 2.
Mod 2, so the parity, whether the number of divisors is odd or even.
Precisely. And when is the number of divisors odd?
Only for perfect squares. We just discussed that.
Exactly. So this formula is summing up 1 for every perfect square up to n and 0 otherwise. It's just another way to count the squares less than or equal to n.
Clever. Using the divisor function's parity. Very neat.
It is elegant.
And one more that looks surprising. A sum connected to log 2.
Yes, from Amiram Eldar, referencing A002162. The sum from n1 to infinity of n plus 1 divided by a equals the natural logarithm of 2.
An alternating series involving the integer square root gives log 2. How?
It relates to how the terms an grow and how often they repeat, interacting with the alternating signs. It connects our sequence to the analysis of series and specifically to constants derived from things like the alternating harmonic series. Quite unexpected.
It really seems to touch almost everything. Finally, the practical side, the prog section, code.
Always useful. Implementations in Magma, PARI, Haskell, Python, Scheme, Julia. Lots of options for students who want to compute or experiment with the sequence.
Yeah, I saw notes about the Haskell using bitwise stuff for speed and scheme avoiding floating point.
Right, showing different computational strategies. Useful if you need high precision for very large n, where standard squirt functions might lose accuracy. It makes the sequence tangible.
So we started with just chopping off the decimal from a square root.
Mm-hmm.
And we ended up talking about counting squares, divisor properties, geometric means, weird number bases, sequence inverses, generating functions, theta functions, the Riemann-Zeta function, log 2.
It's quite the journey for such a, well, seemingly basic sequence.
It really highlights the richness of the OEIS and number theory itself.
Absolutely. For any student listening, A000196 is a perfect example of how exploring even one entry can open up a whole universe of interconnected mathematical ideas. Don't just look at the first line definition.
Definitely dig into those comments, formulas, cross-references. We really encourage you to click around on the A00196 page after this.
And maybe think about this. With all these different ways counting squares, geometric means, divisor parity, the 10n plus 1 repetition to arrive at the same sequence, what does that tell us fundamentally about how squares and divisors structure the integers themselves? What's the core idea these different perspectives are all pointing towards?
That's a great question to ponder. A fantastic reminder that even the sequences that look simple on the surface can be gateways to incredibly deep mathematical insights. Thanks for joining us on this deep dive.